All right, and then today's topic is anaerobic digestion. Certainly, it's been a topic that I think we've talked a lot about in the world of manure for probably 40 to 50 years now. I think the first time this got really popular was in the 1970s, and then I think there was quite a bit of popularity again in the 1990s, and we're seeing a fair amount of interest once again. So I'll try and give a brief presentation on what some of the basics about anaerobic digestion are, and then try and talk through some of why maybe we're seeing a lot of interest again right now. Hopefully Gabby will get here. If she doesn't, no matter what, we will give you a presentation on some economic modeling we did for Iowa specific conditions about what it might take for anaerobic digesters to look feasible, and hopefully that'll give some insight into why people are asking a lot of questions about them again. So as always, if you have any thoughts, questions, something you want to add at any time, feel free to unmute or type into the chat box. We always look forward to hearing what you have to say. So anaerobic digestion. So the process overview, at least how we're going to think about it, is we're going to start with our manure, right, and all the good stuff that contains, maybe some pathogens in there as well, lots of macronutrients, in particular things like that carbon that's in there. That's what we really want: nitrogen, phosphorus, potassium, sulfur, and then micronutrients as well that the bacteria need. I mentioned that carbon, but those unstable organic materials, and that's really, when we talk about anaerobic digestion, what we want. That carbon in our whatever material we're working with, whether it be manure or biomass, is what we're going to try and convert. Put that into some sort of container, get a consortium of microorganisms to work on it. If we compare this maybe with some other technologies that we've seen more recently that people have been working on, cellulosic ethanol, for instance, with cellulosic ethanol production, we're really looking at one specific type of microorganism to try and do our conversion. One of the big advantages of anaerobic digestion is it's this consortium of bacteria, so we don't need to worry to the same level about sterilization, getting things clean, and obviously in the world of manure, that is important to us. This can have some drawbacks though, right? If it's a consortium of microorganisms, they all have to work together and try and accomplish things at the same rate. Sometimes that can be a little harder to accomplish than others. For instance, if we were feeding just manure every day and all of a sudden have an opportunity to take some substrate that some processing company near us is trying to get rid of, let's say food processing waste, and we slug a bunch of that in, it can make our microorganisms really unhappy. And that is often how we get upsets to our digester, where we might see good gas production right after we put it in, and then all of a sudden it really falls off. So it is a team game that makes the biology of the system a little bit more complicated. But for the most part, there's some resilience there where multiple bacteria are trying to do roughly the same process. So they don't like big changes quickly, but it can work out pretty well for us. And then traditionally, the way this is looked at, one of the major benefits was the effluent that comes out is treated and stabilized for us. And that works great when we talk about it as a treatment. For instance, maybe it's pathogen free. I have trouble thinking we'll ever get to pathogen free, but most anaerobic digestion work has shown a good reduction in pathogens. Pathogens are the number 3 or 4 water quality impairment here in Iowa. So they are something that might become more important for us. As we're going to talk about in a few months, they might have some impacts on antibiotic resistance and antibiotic resistant genes in manure. We're trying to do some work here at Iowa State right now, just gearing up for that, to really study that and what we might be able to do about it. But that might be something that people are interested in. That material that comes out often is billed as nutrient rich. That's something that I think we'll talk a little bit more detail about today, because really anaerobic digesters don't remove nutrients, they don't add nutrients. Whatever we put in mostly comes out. So it really depends on what we're feeding for how nutrient rich that material might be. But in some cases, it is more amenable to other treatments or separations to create a nutrient dense fraction. And then one of the more important things is it is often more stable, and that stability can mean something like low odor. In manures, in decaying biological materials, oftentimes much of the odor comes from those carbon materials that aren't all the way processed down to CO2 or methane. Certainly there are other compounds, ammonia, hydrogen sulfide. Anaerobic digestion is going to do little to change how much of those we're dealing with, but it does impact some of those carbon compounds, and with them it might change some of our sulfur compounds from organosulfur compounds into hydrogen sulfide. And by doing that, most of those compounds, even though we think of hydrogen sulfide as having a pretty intense odor, for the most part, those organic sulfur compounds tend to be a little stronger in odor. And the same actually works for nitrogen. While ammonia is relatively smelly, those amines are actually, which is the organic form of nitrogen before we break it down, tend to be a little bit smellier, a little bit stickier. So by breaking them down, hopefully we don't have quite as much odor. And then one of the reasons that we've really seen interest in anaerobic digestion throughout the years was we're talking about energy generation. In the 70s and 90s, that typically meant that we were going to put a generator on our farm, burn that methane, and convert it into electricity. Right now, we're seeing much of the push for anaerobic digestion occurring because people may want to compress it and inject it into the pipeline. There are a couple of reasons for doing this. There is a program called RINS, Renewable Identification Number. Manure that has been anaerobically digested in the methane we generate from it will generate a D3 RIN, which is effectively the good RIN or the more valuable RIN. It says that it is a renewable or cellulosic material that we were digesting. And so that's a government incentive to basically encourage this. And while that RIN is nice, it definitely adds some value to a lot of the projects people are looking at. California, as it often is, has been one of the major drivers in why people are looking at this sort of technology. California has a special carbon SIP program, a low carbon fuel standard essentially for their businesses. So if you can connect to the pipeline and show that you can send gas to California where an end user there would buy it, you can get some extremely nice benefits for what the value is for that credit. For just a point of reference, the value of the California credit is somewhere in the neighborhood of 7 to 10 times the value of the actual methane that we're making. So that is a huge incentive for why people have been starting to look at these types of projects. And one of the key reasons for why we might be getting close to economic feasibility at the current moment. Certainly, we don't just generate methane. We do make other gases like carbon dioxide, hydrogen sulfide. And in order to put it on the pipeline, that biogas needs to be relatively pure. To do that. So when we talk about anaerobic digestion, we're probably in the neighborhood of somewhere between 50 and 70% methane. In order to be able to put it onto the pipeline, we do have to get it to pipeline quality gas, which generally means somewhere in the neighborhood of 95 to 97% pure, depending on the pipeline that you're trying to inject it to. And certainly the area of your country, the region you're in, and the actual pipeline that you're injecting to all set some quality standards. But we do have to monitor all our injection points to meet that quality standard. So one of the more expensive parts of anaerobic digestion today, just in addition to having to put a digester on your farm, is really the biogas cleaning system that you have to put on and that injection pipeline. We haven't put in too many injection pipelines. I've been involved in a couple digester projects where they have put them in, and we're talking somewhere in the neighborhood of $1 million to $2 million to make that hook up to the pipeline. So definitely not a cheap investment, something that it does take a little time to recoup. When we talk about the anaerobic digestion process, it occurs in a couple stages. The first one is hydrolysis. So when we're working with manures or biological materials, we often start with really complex, big organic stuff, and we want to break that down into stuff that bacteria can actually get in their bodies. So we want to take some of those bigger materials, turn them into sugars, amino acids, and fatty acids. Coliform bacteria are generally some of the more involved organisms in that breakdown, but it tends to be the first step. Oftentimes with manures, that is the rate limiting step, which probably doesn't come as too much of a surprise, right? We've already digested much of the material once as it went through the animal body. So what we're left with is a little bit harder to break down. And because it's harder to break down, it does tend to be the slower step in the process. Because of this, you might see people use more sophisticated digester designs. In practice, we haven't seen a whole lot of that yet, but some more sophisticated designs where we might be at a higher temperature for the first stage of digestion before it goes into a main digestion unit, or especially as we look towards some more complex biological materials beyond manure, let's say corn stover or switchgrass or prairie grass, they might be looking at hydrolysis units where they're doing pre-treatment before it goes into the digester. The second stage is acidogenesis. So that's taking that simple molecules that we made and breaking them down into ammonia, carbon dioxide, hydrogen sulfide, and it's acidogenic bacteria that perform this. And it's really those two processes that get us started. Right after that, we make acetogenesis, and that's really taking the acids that we make and trying to turn them into carbon dioxide, hydrogen, and really short chain VFAs. So acetic acid, propionic acid, butyric acid, rather than longer chain carbon compounds. Some people try and stop the digestion process roughly there. Mostly that's been done on the research side because some of these carbon materials can be building blocks for more complex molecules or other liquid fuels. The disadvantage of that is separation of that stuff is really hard. And one of the huge advantages of AD is by making a gas product, separation from our manure is really easy, right? It's naturally going to bubble out, get to the surface, and be released. So we get a relatively clean fuel that we don't have to do a lot of work for separation with. And then the fourth step is methanogenesis. And really that's taking the carbon dioxide that we've generated, reacting it with hydrogen, or taking acetic acid that's floating around in that digester and having methogenic bacteria break it down and turn it into methane. All these steps have to be in balance. If any of the steps gets too quick, we tend to see issues. For instance, when we take easily degraded materials, for example, food processing waste, and slug it into our digester, one of the things that we tend to see happen is the acidogens and the acetogens work much more quickly. They respond much more quickly than the methanogens. So we're going to end up starting to make lots of VFAs. We'll see those volatile fatty acids accumulate, and just like their name implies, they're an acid, and we'll see the pH of that digester drop. If the pH drops too far, we'll get what we call the digester has soured, and it takes a long, long time for it to catch up. Most of the time it takes some intervention from a person to get us back on track. And the reason that happens is because methanogens are extremely sensitive and tend to grow relatively slow. For the most part, if we operate relatively stable, right, where we add the same amount of food every day, the same type of food every day, these systems tend to self-regulate. But if we have some strange event where we slug loaded something in, we can get a hang up in the system, right? So if we sour it, we did a bunch of these steps, made our volatile fatty acids, and then we hang up right there. In some cases, right, if we're trying to capture VFAs, some people have tried to encourage that. Oftentimes that leads to difficulties though. Okay, so what are we making when we talk about anaerobic digestion? We end up with two phases coming out, right? This biogas phase, that's what we were trying to create most of the times in these energy projects. And that methane content is typically 55 to 75% methane. It depends a little bit on whatever substrate you're starting with and the pH that you end up sort of operating at. The remainder of whatever we have in there tends to be mostly CO2, a little bit of ammonia, and a little bit of hydrogen sulfide. In some cases, there will be N2 gas as well. That would tend to imply that we're leaking something into our digester as we're feeding, right? So if we have something where we have some gas bubbles in it when we start, we might have some air, some N2 in there. N2 is extremely hard to separate. So oftentimes people who have put in covered lagoons and tried to do these anaerobic digestion projects, especially in spring before we start making much biogas, tend to have a fair amount of N2 in their gas. Since it is so hard to separate, they have trouble making pipeline quality gas to start with until they've worked that N2 through the system. Just for a couple points of reference, methane is colorless, odorless, and highly flammable. So the advantage of it being odorless, just like CO2 being odorless, if we actually can get complete anaerobic digestion, the carbon compounds that we're making don't have any odor, right? So that can help out some odor challenges on our farm. But we do have to get relatively pure hydrogen sulfur or methane to put it on the pipeline. So when we talk about energy density, and I think this is something that we talked a lot as we started adding ethanol to our gasoline fuel, right? When you think about fuel densities, gasoline is somewhere around 46 megajoules per kilogram. ethanol is a little lighter, right? So as we think about putting it in, we only get 30 megajoules per kilogram. So when we talk about maybe getting less fuel mileage with a gallon of ethanol, we have a little less mass there. Their density isn't that different though. So there's less energy in a gallon of ethanol as compared to gasoline. Methane, on the other hand, is more energy dense when we think about it in terms of weight, but methane's not very dense at all, right? It's a gas. So when we start thinking about what that might mean, it doesn't work for a transportation fuel unless we really can pressurize it and condense it. So your comparison there is on the bottom. Like I mentioned, there's CO2 in that gas. The CO2 is essentially zero energy content. It does take a little energy if we were doing direct combustion on the farm trying to make electricity. It does take a little bit of energy to heat it up. So it is a waste in the product. Same way with water vapor. We've tended to do good separation these days, or relatively good separation of water vapor before we combust it in a boiler. But they are sort of parasitic in that system where it takes some energy to warm them up rather than getting energy out of them. Hydrogen sulfide contains good energy, right? So even if there is some in our gas, when we burn it, we'll still get decent energy. It is stinky. You can't really detect it. And the big problem there is when we burn sulfate, it makes sulfuric acid. So if you don't remove hydrogen sulfide before you combust it on your farm, it does tend to cause some issues in your generator where we're eating it away with sulfuric acid. Oftentimes people who have tried to use this gas for boilers have maybe not done as much cleaning to get it to as pure of quality, knowing that their boiler will suffer some damage from hydrogen sulfide, that sulfuric acid generation, and hoping that the cost of not cleaning more than makes up for the shortened life of the boiler. But that's sort of a farm or process decision on any specific farm. The other thing we end up with is that liquid digestate. Typically, it's relatively nutrient rich, especially if we start with something like manure, but it is definitely not to the point where we're going to ever be allowed to discharge it into a water body. It will take further treatment or land application to dispose of it. When we think about some real big advantages of anaerobic digestion as compared to cellulosic ethanol or other energy generation processes, it doesn't need sterilization, right? We're going to need bacteria, so we don't have to do much for cleaning, and that makes it very amenable to taking a wide range of products, swine manure, poultry manure, cattle manures, corn stover from our field without any cleaning. So that is a huge advantage to us. The second one is product separation, right? It's really easy to separate that gas from the liquid, so we don't have to use sophisticated systems. If you've ever seen the cellulosic plant that they're building here near Ames, to separate their ethanol that they generate from all their liquid product, they had built really large, really expensive distillation columns and condensing columns, right? So we don't have to invest in that sort of technology to get there. And despite the fact that later we'll talk about that we've seen a fair amount of failures of anaerobic digesters, it is relatively simple equipment and operation. Certainly, I don't mean to minimize the challenges that you can have in these systems. There are many of them, but in comparison to maybe some of the other energy generation systems like cellulosic ethanol, it is a little bit simpler. The big challenge that we've always had with these systems is, can we compete with other energy sources? And we talked about electricity earlier. For the most part, people struggled to operate these systems in a way where they competed economically. And with compressed natural gas, certainly it's provided a new opportunity. For the most part, we'll have the same discussion. Can we compete economically with relatively cheap natural gas? Especially as we were fracking, we saw some challenges to meeting that. And the only thing that really makes us cost competitive now is government incentives, whether it be that RIN credit or programs like the California Low Carbon Fuel Standard. Some disadvantages of anaerobic digestion: reaction rates are relatively slow. That tends to mean we need relatively big vessels on our farm, and that still adds up to some pretty good capital cost. Installing a digester probably is going to cost us in the range of $1 million to $2 million on a farm when we get towards that economically feasible size, maybe sometimes even larger. Methane yields are relatively low, right? So that's the product we want to make. More is better, but even though we can get some conversion, it's not always super high amounts. And then conversion times, like we mentioned, is relatively long. It's not a day, it's not 2 days. Typically when we talk about manures, we're in the neighborhood of that 28-day or somewhere around a month-long retention time in our digester to get the conversion we need. And then obviously gas cleaning and corrosion issues are important, and certainly we've seen some technologies to help us along the way with that. The only reason we can have the compressed natural gas discussion right now is technologies like pressure swing absorption or membrane separation technologies have really put themselves in a marketplace where they can clean the gas for roughly half the price to the value of the natural gas as we put it on, depending on sort of your project size. So all of a sudden we can start having these conversations about what does a farm need to look like to be economically feasible. And then the last thing I wanted to talk about before we move to some economic modeling was estimating gas production, because really the size of your project is one of the most important variables to making these things go. There are a few ways to estimate the amount of methane we'll make. One of the easiest is based on the amount of COD, chemical oxygen demand we have in manure. The harder part there is you do need to estimate some COD conversion percentage, and that's a little bit different for every substrate. It's a little bit different depending on what our manure looks like, but I do have a table here for you that comes from a great NRCS document that I'll make sure we get shared on the image webpage about what sort of percentages of COD conversion you can anticipate. And I think one of the big things here you'll see for swine is the COD conversion is actually relatively high. When we talk about how much biogas we're making, we estimate somewhere around 33 cubic feet per animal unit per day, which actually makes us relatively comparable to dairy operations where we've tended to see more of these digesters installed. The other way to estimate biogas production is with the biochemical methane potential. Basically, it's a lab analysis where you digest the manure as completely as you can, and they see how much methane they made from a sample. It's a lot better estimate than using table values for the same reason that actually taking a manure sample gives us a better estimate about how much nutrient we're actually going to be applying from our field. But it does take a little bit of time. Oftentimes those tests take somewhere around a month to complete because we do want to get that complete digestion, but it is a much more specific answer to an individual manure. So with that, we'll take a brief break as we switch some presentations. I see Gabby has joined us, so hopefully Gabby can unmute.
Yes, I can unmute.
Beautiful. And if I stop screen sharing appropriately, you can hopefully be able to share your screen.
All right, let's see that.
And while Gabby's doing that, I'll give a brief introduction. Gabby is a graduate student pursuing a PhD here at Iowa State University under the guidance of Dr. Rahman and myself. I've been really lucky to work with Gabby. She is a great student. As an undergrad student, she did some economic modeling for us on a few projects, anaerobic digestion and biogas production being one of them. And currently she is transitioning into doing some water quality work with manure for us up at the Nashua site, looking at some different cover crop treatments. So Gabby's been a great asset to our team. I think she's a great asset here to Iowa State University, and she's going to talk you through some biogas production cost modeling that she did with us to try and figure out what kind of farm could these systems be put on in Iowa? What would that sort of system be? What would it look like? So by no means do we think this is the answer to all the questions, but it does get the conversation started about what we see as some potential opportunities and some potential challenges. So with that, Gabby, take it away.
All right. So yeah, like Dan said, we made this biogas production cost model. Just a brief introduction, we focused on swine manure instead of beef or dairy cattle like we normally see. And instead of focusing on using biogas to produce electricity, we actually looked at how it could compete with natural gas instead and for use off the farm, specifically as a transportation fuel so we could utilize those RIN credits. Also in our model, we look at the impact of using corn stover along with swine manure to maximize the methane production potential, and then different levels of centralization to see if it could be viable at a single farm or if multiple farms need to work together in order to make the system economically viable. So in this presentation, we have 4 scenarios. The first scenario is a water limited co-digestion farm scale scenario. So this would just be a single farm. There's no additional water added. So not as much biomass can be included in the digestion. And then cleaning and injection into the natural gas grid would take place at the farm. In scenario 2, we consider in a water addition to the digester that's equal to the volume of manure. So that would allow for more corn stover to be added to the digester. But otherwise, it's the same as scenario 1. In scenario 3, we consider centralizing the biogas cleaning and injection site. So in that scenario, 5 farms would share the cleaning point for the biogas. And then in scenario 4, we consider a community scale digester. So that would be shared by 5 farms. So it would handle the manure of 5 farms, but everything would take place at that centralized facility. So just another description of the scenarios. So in scenario 1, it's a single digester and it would need to pull corn stover from 125 acres. In scenario 2, because of the water addition, the land needed for the biomass is higher at 500 acres. Scenario 3 requires the same amount of land for each farm that scenario 2 does, but there's a centralized cleaning point for the biogas, so they share that cost. And then scenario 5 has 5 farms that transport their manure to a centralized digester. So this slide just shows some of the key assumptions that we put into our model. So we assume for all scenarios that the swine manure would cost $5 a ton, corn stover would cost $20 a ton, and the maximum amount of solids you could add to the digester would be a 12% solid. For the farm size, we assumed 4,800 head farms in each case. And then for biogas and manure transport, we assumed that it would be 2.5 miles. That manure transportation cost would be about 1/3 of a cent per gallon per mile. The capital cost was scaled using a 0.6 scaling exponent, assumed 20 years loan and at 7% interest. And then for credits, we assumed that you would get some money back for the digestate or digester effluent. And then we also considered the D3 RINs, which we used a 3-year average from 2017 to 2020, and that's $1.92 per gallon of ethanol equivalent. We also show at the end of the presentation a different cost for RINs and a 0 interest scenario. So for each of the scenarios, we compare to the Iowa Citygate natural gas price. So that's $4.63 per gigajoule. But you can see kind of how that's changed since the 80s in this graph. So like I said before, because corn stover has the higher methane production potential than swine manure, we tried to maximize the amount of corn stover that could be added to the digester within the 12% solids limit. So to calculate the water addition needed to meet this, we wanted to make a land balance between the corn stover harvested and the land that would be needed to apply the digester effluent as fertilizer. So these are kind of the assumptions that went into that. Then we assume that the manure would be produced at 1.2 gallons per head per day with a 0.05 pounds of nitrogen per gallon, and that we would harvest corn stover at 3 tons per acre. And then we assume that the digestate would be applied to the land as fertilizer at a rate of 150 pounds per acre. So this slide just has the results of that analysis. So the biomass demand ranges from 375 tons per year to 7,500 tons per year. The land requirement for that ranges from 125 acres to 2,500 acres. So that ends up being 19% to 77% of the land is needed to harvest biomass from the land that you would require to apply the digestate. So this is the results of the first scenario, which was the farm scale digester. So it ends up about, after credits, costing about 2 times the cost of natural gas in Iowa. But that's after considering the RIN credit. So before any credits at all, it's quite a bit more expensive, about 10 times more expensive than natural gas. So scenario 2, this is where we added water so we could maximize the corn stover input and the methane production. So this scenario is actually less expensive than natural gas in Iowa by a little bit. It's about 93% of it. The share of costs changes a little bit. The biomass makes up 8% of the total cost instead of 3% of the total cost in scenario 1, just because you're adding more. Scenario 3, so this was the centralized cleaning and injection point. This scenario was actually not any better than scenario 2, so that led us to think that sharing the centralized digestion point was not worth it. It becomes more expensive than natural gas in this scenario. And the capital cost of the pipeline that would be needed to transport the natural gas makes up about 19% of the total production costs here. So in the last scenario, this was the community scale digestion where manure would be transported to a centralized digester. So this is the most competitive scenario. When you consider the RIN credits, the cost is negative, so you could make a profit here. So that just shows that the manure transport, it's less drastic than the like scaling advantage you get from scaling up the digestion process. So I'm looking at this and I did not update this graph, so these are the wrong numbers, I'm sorry. But you can see that the centralized cleaning scenario, which is scenario 3, did not have any advantage over scenario 2. So you would be better off just having a totally decentralized digester than sharing the injection point. But the community scale digestion is still the most cost effective. In this slide, we show the zero interest scenario. So this was the same as scenario 4, but we assumed that there was some government program that allowed the capital costs to have no interest. So it's a lot more, it's about $8 per gigajoule below production costs after you consider RIN credits. And here the capital cost makes up 25% of the cost instead of 40% of the cost that it makes up in scenario 4. So that could be a way for producers to be able to get that capital covered, because it would be a lot for this centralized scenario. So here is all of the scenarios compared to the cost of natural gas. So like I said before, scenario 4 is the most competitive option. The benefit of the economies of scale you get from centralizing production outweighs the cost of manure transportation that you have to do in that scenario. But scenario 2 is still competitive with natural gas without centralization. So in this slide, I show the difference between the two types of RINs that biogas can qualify for. So D3 RINs are what agricultural digesters qualify for. So that average price was $1.92 for 2017 through 2020. But the blending volume could accommodate about 1,000 of these scenario 4s that we have, which is about 80% of swine farms in Iowa. So the other type of RINs that biogas sometimes can qualify for are D5 RINs, which are advanced biofuels. So some types of waste digesters will qualify for these, and they have a lot lower average price. So this slide just kind of shows that the price of the RIN is very important to whether or not the system can be competitive. So when you go from the $1.92 for a RIN in D3 to the 58 cents, you're way above the price of natural gas. And for the D5 RINs, that's about 3 times the price of natural gas in Iowa. So it's no longer competitive. But the volume could accommodate more swine farms and about 8,600 of our scenario 4s. So this slide shows the RIN price over the past 7 years. So you can see that for D3 RINs, there's been a lot of volatility. And that is concerning if you were going to be dependent on this, because a 10-cent change can cause a $1.23 change in the overall price of your biogas or the production cost. So the cost is very dependent on these RINs, so the volatility is a concern. Another concern is reliability. So since 2000, about 25% of the total anaerobic digesters on livestock farms have been shut down. But most of these are single farm digesters where a farmer is doing all of the work for the digester on their own. So we think that maybe a scenario 4 type of system would improve the reliability because specific staff could be hired to run the digester. It wouldn't be just the job of the people at the farm, kind of relieve them of that burden and maybe make the digesters more reliable. So in conclusion, you can see that maximizing corn stover input was needed to bring the production costs down to competitive with natural gas. The costs of biogas transportation in the shared cleaning scenario was too much to make it competitive with the totally decentralized scenario. Overall, the centralized digester was the most competitive, and any chance of economic viability is dependent on government programs like RINs or zero interest loans.
Perfect. Thank you, Gabby. I really appreciate the work you put into building that model and presenting it. I think one of the challenges has always been identifying farms that might be a fit and what it really takes to make these systems work. And I thought your work helped really make that clear.
Thank you.
So with that, we'd definitely like to open it up for any discussion or questions people may have. Feel free to unmute and ask them or type them into the chat box. And we're not going to get any questions, I think, which is perfectly okay. I will say I do appreciate seeing Mark Garrison here. I know Mark did some work with anaerobic digestion back when he was working on his master's degree. So certainly He has some great experience on some of the challenges and struggles that we can face along the way. We did not get into the regulations today about when is it an anaerobic digester, what does that mean for effluent application considerations, what happens if you take other byproducts from processing plants, what do the regulations look like? That could be a conversation in and of itself, but certainly as we think about some of these projects, something that we would have to consider. I think one of the important take home from Gabby's modeling work is that while oftentimes we've said these digesters only fit on relatively large farms, you can see if you would start looking at potential to blend manures with biomasses, some standard size swine farms, right, 4,800 head finishing operations can start to look economically feasible. Certainly their absolute distance from the pipeline, depending on how that compared to what we modeled, or the ability to build a community digester and work out manure sharing agreements, could add some complexity to these systems. But one thing that we do see is that we're in the neighborhood where these systems start to look feasible and could work. And that's one of the key reasons why we're seeing a lot of interest in these systems in neighboring states and potentially in Iowa. The other thing I will mention is that in our work, Gabby and I did not include the California low carbon fuel credit in our work here, because that is set to expire next year, and I didn't want to project the tea leaves on where that would go. But again, the California credit is somewhere in the neighborhood of 4 to 5 times what that RIN credit is, which really makes many of these systems look more favorable than what we presented, presuming that the California credit gets renewed and we can all still capture it. The California credit is dependent on species and what your original methane production would be from your manure storage. So swine and dairy farms tend to benefit from that rule. Beef and farms not nearly as much. I can talk to you about more details on that if anyone would like them, but we'll take that offline. The same way goes when you're collecting a D3 and D5 RIN. EPA was not approving process pathways for a little while, so there are some questions about how different agricultural residues would qualify within that system. But with that, really thank you all for joining us today. We will have next month off, but we hope to see you again in July when we talk about odor control and bring back Dr. Steve Hoff. So thanks everyone for joining.